Welcome back. This is Lesson 5 in Unit 3 of our AP Calculus course. Today's lesson is one of the most important lessons that we'll ever have. It's on the chain rule. Understanding the chain rule is going to be absolutely essential to your success in AP Calculus and in future math classes. So let's get going. Given two functions, f of x and g of x, the composition of these two functions is written as f of g of x. We learned this in our pre-calculus classes. Examples of composite functions would include the following. So I just made up a couple here. 2x cubed minus 1 to the fourth would be a composite function because I got 2x cubed minus 1 inside a fourth power. Let's see here. G of x equals sine of x squared plus x. That's also a composite function because I've got x squared plus x inside a sine function. So it's just about having one thing inside of another. Now, to find the derivatives of these composite functions, we have to use the chain rule. And this is the chain rule. The derivative of f of g of x is f prime of g of x times g prime of x. In other words, we take the derivative of the outside and we leave the inside alone. Then we multiply by the derivative of the inside. And we may have to keep doing that time and time again as we work our way from the inside out. So here is this. You take the derivative of that and you keep the inside exactly the same. Then you multiply by the derivative of the inside. For a proof of the chain rule, we'll do that at the end of this lesson. All right, so let's find the derivative. So to find the derivative of this function, I'm going to say f prime of x. I bring this, so what I need to realize I need to do is take the derivative of the outside. So this outside thing is something to the fifth. So I bring down the 5, and I keep the inside exactly the same. Make no changes. And subtract 1 from the exponent. So that's our normal power rule. But now I have to multiply by the derivative of the inside. And most of the time you're going to need parentheses. So the derivative of the inside, 3 comes down, I get 15x squared. Minus 2, because the derivative of 2x is 2, and the 1 goes away. So that's the derivative. Yes, we could have multiplied that out and tried to multiply that 5 times, but that'd probably take an hour. So this is definitely the right way to go. And more often than not, you have no way of expanding it. Like in the very next problem, actually. So would you please work this practice problem? All right, let's see how you did. So you could write dy dx or y prime. We're going to bring down the exponent because we're just doing the power rule here. Then we have x cubed over 5 plus 2. And that's going to be raised to the negative 1/3 power. Now I got to multiply by the inside, making this 3x squared over 5. And the 2 goes away. And there we have it. All right, you try the next one. Find the derivative of this equation. Okay, hopefully you realize that you're going to need to use both the quotient rule and the chain rule here. You could also use the product rule if you move this up to the top. But I'll use the quotient rule. The quotient rule says low d high minus high d low. Now here comes the chain rule. 2 times 2x minus 3 to the first times the derivative of the inside, which is just a 2. All over low, low. Okay? All right, I got some more for you. So let's try g of x. Find the derivative of g of x. All right, first thing I would do is I would rewrite this because I don't like radicals in my calculus. X squared plus 1 to the 1/2. All right, let's use the quotient rule. and apply the chain rule as necessary. So the quotient rule says low d high minus high d low. So I bring the 1/2 down, and the inside stays exactly the same. Subtract 1 from the power, and now I multiply by the derivative of the inside. All over low, low. And that just becomes x squared plus 1 to the first. All right. Okay, for letter B, try and find the derivative of this. Remember, take the derivative of the outside, and then the inside, we multiply that by later. Okay, so hopefully you did this. The derivative of sine of x squared plus 4x minus 5. So the derivative of sine is cosine, and the inside stays exactly the same, times the derivative of the inside, which is 2x plus 4. Okay? Cosecant x squared. All right, would you take the derivative of that, please? All right, so hopefully this is what you did. The derivative of cosecant is negative cosecant cotangent. Or we would say, we're going to say cosecant u is negative cosecant u, cotangent u. So that stays exactly the same. Then cotangent, and it stays exactly the same, right? That's just doing the cosecant part. Now I multiply by the derivative of the inside, which is 2x. All right, let's do another one. Tangent of x squared times sine of x. All right, so you could have said y prime is equal, we know that the formula for tangent is secant squared, so it's secant squared x squared sine of x. Now I got to multiply by the derivative of the inside, which will require the product rule. So I do derivative of the first times the second, plus the first times derivative of the second. And there we have it. All right, I'd like to do a few more examples. I really want to focus on the trig and how that works, because that can be a little bit weird at times. So we'll start with the simple example. The derivative of sine of 3x is f prime of x is equal to the derivative of sine u is cosine u. Oops, I literally wrote u. I mean whatever u is, 3x, times the derivative of the u, derivative of the inside. So you'll hear me say the derivative of sine u is cosine u times u prime. All right, let's take a look at the next one. This next one's a little different. We have sine inside a square root. So I have the sine of x squared inside a square root. So on this one, we have f prime of x. All right, so this 1/2 power, I used a power rule, so 1/2 times sine of x squared to the negative 1/2. Then I multiply by the derivative of the inside. The derivative of the inside is the derivative of sine of x squared. Well, that is cosine of x squared. But then I got to take the derivative of the inside of the x squared, so it's times 2x. So you see we did a chain, and a chain, and a chain, right? We had to take the derivative, chain rule, chain rule. All right, let's do another one. Cosine of x plus 1 over the square root of 2x minus 3. So dy dx is equal to the sine. The derivative of cosine is negative sine. And this stays exactly the same. Then I multiply by the derivative of the inside, and we should have probably rewritten that as x plus 1 over 2x minus 3 to the 1/2. So I'm gonna do that right here. There we go. Now I have to multiply by the derivative of the inside, so I have to use the quotient rule. So that's low d high, the derivative of the high here is 1, minus high d low, which would be 1/2 times 2x minus 3 to the negative 1/2, times 2, because of the chain rule inside there, all over low, low, which is 2x minus 3 to the first. That's a pretty big one. Look at how big that expression got. But that's what can happen. All right, let's do a couple more. So remember that when you have sine squared, that squared is actually on the outside. So this is kind of a lazy notation, and it's really confusing when doing calculus. So for a while, until you get really used to it, when you see something like that, I want you to do this. I want you, because that's what that's really for. That's just shorthand for that. Now it's going to make it easier for us to take the derivative. We can see that this is a power rule, and this stays exactly the same to the first power, so I don't need the exponent anymore. Then times the derivative of the inside. The inside of this is cosine x cubed plus 1. Then times the derivative of the inside of the cosine, which is 3x squared. All right, let's do another one. The tangent to the fourth of negative x. Let's rewrite that first off as tangent of negative x to the fourth power. And then we'll say f prime of x is equal to 4 tangent negative x cubed. And I could put the cube there if I want now, but I'll leave it on the outside. The derivative of tangent is secant squared u times u prime. Now that we have the chain rule, I think it's important that a couple of things you have to realize. One, the chain rule has always been in effect. We just haven't had it make a difference yet, but it's always in effect. Even if on something as simple as x squared, the derivative with respect to x there of x squared is equal to 2x times the derivative of x. What's the derivative of x? 1. It's always been there. It's just eventually it becomes 1. So there is no time where, should I use the chain rule or not? It's always chain rule. Always. Okay? And from now on, I'm going to make that clear. I want your formulas to be memorized like this. So I've given you incomplete formulas thus far. Here's a more complete formula list. And you know that u prime is the same thing as du dx, right? So a lot of times you'll hear me just say it or even write it. Like I might say that the derivative with respect to x of sine u is cosine u prime. But I went ahead and wrote them with du dx here just to, I don't know, because I thought they looked more professional, I guess. But but no, you can just say u prime. So here's our power rule. Bring down the power, multiply by the derivative of u. Derivative of sine u, the full formula is cosine u prime. Tangent u, secant squared u prime. And so forth. So it's important to know those. All right, so that's the chain rule. Now, question is it real? Right? I mean, how are we going to know that this is a real thing? Well, we're going to know because we're going to prove it. All right? We're going to prove that the chain rule is real. If you are not interested in such things and just want to take it on faith, I guess you could stop the video now. But for those of you that are more mathematically curious, let's go through this together. So we're going to take the derivative with respect to x of f of g of x. That's what we're going to do. All right, well, we know that is equal to, there's a couple different things. I could use the limit definition, but I'm actually going to use the alternative limit definition. So I'm going to take the derivative as x approaches a of f of g of x minus f of g of a all over x minus a. Now, when you use the alternative definition to get a derivative formula, that means you're not taking the derivative at a real number. We're taking it like at a value a. You're going to get a formula for the derivative in terms of a. So, but it's still the same thing. It's just, then you can swap out the a's for x's or what n's or t's or whatever you want it to be. All right, so that's our formula for the derivative. Now, here's the deal. There's really two cases to this proof, and the second case is pretty much trivial, but I do want to make this point. I don't know if we'll even go over the second case, but I'm going to assume that g of x does not equal g of a. All right? And what that means is that as x gets arbitrarily close to a, g of x and g of a are different numbers. If they are not different numbers, then I can't do what I'm about to do. And we can discuss what we would do in that situation, but that's a very unusual situation. So in general, g of x will not equal g of a. Well, if that's the case, if g of x does not equal g of a, then doing this is a perfectly reasonable thing to do. Multiplying by g of x minus g of a over itself, right? That's totally okay because g of x and g of a are not equal, so I'm not dividing by 0 here. All right, now what I'm going to do is I'm going to just use the commutative property of multiplication, and I'll leave the top the same. And I'm going to put g of x right here, over here. And this will be g of x minus g of a over x minus a. Now, using the limit properties, I can just take I could split limits up around multiplication. So I've really got two different limits as x approaches a. So what is this? Well, that right there is x approaches a. That is just f prime of g of a. Okay? So look at that and think about it. See, that's what that is. That's, I could let, as the limit as x approaches a. I'm also having to use the limit of a composite function rule. But basically, it just says that I can take the limit of the inside and put it on the outside. But as x approaches a, then g of x approaches g of a, right? So this is really just saying the same thing, except for instead of f prime of x, it's f prime of g of a. But what is this over here when I take the limit as x approaches a? Well, that's exactly g prime of a. And if we just do a variable substitution to make it look cooler, we can just call this f of g of x times g prime of x, which was exactly what we were trying to show. So what about the other case? And I'll leave you to finish off the second case to write it down formally. But if g of x is equal to g of a as x approaches a, then what we have is a horizontal tangent line. In which case, the derivative there is 0. And so we would expect that f of g of a, according to our formula, since we have f prime of g of x times g prime of x, so if g of x is equal to g of a as x approaches a, then we know that g prime of x must be 0 there. So then whatever this other thing is, doesn't matter. It's times 0, it's 0. And when you let g of x equal g of a, you'll get exactly that situation. You'll get that you'll have a limit of a true 0 because you'll have an f of g of x minus f of g of a actually equaling 0 over x minus a, which is that limit equals 0. So it ends up working that in that case as well. All right, well, that's it for the chain rule. You just got to practice. In the next lesson, we'll look at applying it some more.